Hello everybody, welcome to part B of chapter 1.2. Today we're going to finish discussing the different ways that a limit can fail to exist, and then we're going to briefly study and use a formal definition of a limit. Alright, let's get started. The first topic I'd like to talk to you about is oscillating behavior. Oscillating behavior. And we'll go through an example to really get this point across. So, our example is discuss the existence of the limit as x approaches 0 for the function sine of 1 over x. Okay, now if you try to graph this in your graphing calculator, let's go through that real quick. Hopefully we'll have a little bit better luck with mine tonight. Okay. Let's try this. So we'll go to y equals, and there we go, that's a little bit clearer. Okay. We'll type in sine of, I just had it, it worked out so well. Okay, there we are. Sine of 1 divided by, and we press x. And then if we press graph, oh, I need to fix my window. Well, give me a minute, I'll do that. That is not showing me what I want to see. Okay. I'm going to press zoom, and I'm going to press 6 for Z standard. And let's try that again. Okay. So you can see it does something kind of interesting here in the middle. Let's zoom in there to get a better look. Alright, it looks like it kind of goes up and down in the middle. That's kind of interesting. Here's the thing. What this graph actually does in the middle here, and we'll explain it numerically in a second, is it oscillates, which means it goes forever up and down between two y values. And the thing is, this graph is not correct because in the middle there are actually infinitely many ups and downs between +1 and -1 as we get closer and closer to 0 between the intervals pi over 2 and negative pi over 2 and positive pi over 2. Or pardon me, that's the wrong interval I just said. Negative 2 over pi and positive 2 over pi. That's what I meant to say. So from negative 2 over pi to positive 2 over pi, it infinitely does this, goes up and down. And we'll numerically explain why that is. So, numerically, you could set up a table and you could see this, or we could just kind of think about it. And I'd like to go through the thought process with you. So, I'm just going to title this numerically. And let's think about what would happen numerically here. Here's what we know about sine of x, for example. We know that sine of x equals 0 when x equals any multiple of pi. So I'm just going to write k pi. And a little semicolon, and that just means any multiple of pi. So pi, 2 pi, 3 pi, 4 pi, you get the picture. All of those multiples of pi are going to make sine of x 0. So if we kind of follow that logic, sine of 1 over x is equal to 0 when x is equal to anything 1 over multiples of pi. So if we had, for example, 1 over pi, 1 over 2 pi, 1 over 3 pi, 1 over 4 pi, and we just kept going, we'd always get 0. And remember, the nature of sine is to go up and down, up and down, up and down, and it'll cross at 0, but it'll go up and down between positive and negative 1. And that's what sine of 1 over x does as well. It'll go up and down between 1 and negative 1. What's interesting, though, to notice here is that we're not looking at whole number values for x when this function equals 0. We're looking at fractional values of x. So, if we were trying to find the limit as x approached 0 for our graph sine of 1 over x, as our x values got smaller and smaller and smaller and smaller, we'd be able to fit more and more of these zeros, wouldn't we? So, here's what the graph of sine of 1 over x looks like. It's kind of interesting. Here we are between positive 1 and negative 1, like we talked about. It's going to go up and down between those. And we'll call this negative 1. We'll call this one positive 1. So, it sort of swoops down, reaches negative 1, and comes back up, crosses for the first time at 0 at our 1 over pi value. And then it does so again pretty quickly. And then it does it again even quicker. And then again even quicker. And again even quicker and quicker and quicker. And do you see what my pen is doing here? Oh, pardon me. This needs to go all the way down. There we go. Okay. All the way down between negative 1 and 1. And do you see what happens? As we get closer and closer to 0, we're able to fit more and more of these 0 happenings in, right? Sine of 1 over x is going to cross that 0 line. It's going to go between 1 and negative 1 more and more often, because as these fractions, as our numbers get smaller, we're able to fit infinitely more of these fractions in as we get closer and closer and closer to 0. So we fit more and more of those swoops between 1 and negative 1. Crossing over 0, crossing over 0, crossing over 0. And it just keeps happening when we reach a positive value as well, until again we cross that x-axis at positive two over pi again. And it swoops down once more. And here we are again. And this isn't quite to scale. This should be scooted over just a little bit more, but that's all right. And then we come back around. And what it's called when our graph does this, when it goes up and down, up and down, up and down, it's called oscillating behavior. So let's actually define that formally. Oscillation just means fluctuation between two values. So as we discussed, a limit cannot exist unless values unless the graph approaches the same value from the left and from the right. But if you have something like unbounded behavior, or if you have something like a jump or a gap, or oscillation, then it turns out your graph never actually reaches one value from both directions. And so when that happens, our limit doesn't exist. So we could just simply say the limit x approaches 0 for the graph sine of 1 over x does not exist because it oscillates between -1 and 1 on the interval give me 1 minute. One over pi, -1 over pi to +1 over pi. Okay. And here are some basic situations which describe most often when limits don't exist. So let's discuss those. We'll just say common types of behavior with non-existent limits. We'll underline all that. Okay. The first situation is when f of x approaches different values from the left and right of C, of that value you're trying to find. And the next situation is that f of x increases or decreases without bound as x approaches C. And again, this is visually we can think about asymptotes, right? That example that we did in the last video, we were approaching an asymptote as we were approaching the C value we wanted. And whenever that happens, we're increasing or decreasing without bound. So we're never actually approaching one value for a graph. The last reason is what we just discussed. This happens when f of x oscillates between two fixed values as x approaches C. Alrighty. Let me see if I can zoom that in a little bit better. Does that help? That makes it worse. Does that help? Maybe it's as good as it's gonna get. Alright, that's fine. Okay, moving on. The next thing we're going to talk about, the last little example I have to do with you right now, is using the formal definition of a limit. Now, I'm going to warn you, this is not a very easy concept to grasp. It's not a very simple one. However, we're going to do this example now. We'll do another example in class to start us off. And I would like to give you some reassurance. This isn't often going to be a method you're going to be asked to use in order to find a limit. In order to find a limit, we're going to do those things that we've done in the last video, which are much more conceptually appealing, right? They're a lot easier for you to go, okay, I can imagine what's going on there, right? Where we look at a graph or we look at a table. This stuff, what I'm about to show you, you're not often going to be asked to use it to find a limit. We might use it to prove certain theorems in the future. Just hope that reassures you, and then just bear with me as we go through this. Alright, so to begin, what I'd like to draw for you guys is a little picture. So we'll just draw a little box right here. Okay. And then say we had a graph f of x, right? This curved line. Cool. And then we had that point on that line. And say this is what we want to find. This is the point that we want to find the limit of. And we're going to call this point C, comma, L. As x approaches C, our limit is here, right? That makes that those are the x's and the y terms we're using, C and L. And we can just draw some lines down. So we can see that this point here, we would call this our C value on our x-axis. And then if we made a line, dotted line out, that would be our L value on the y-axis. And here's the thing. Here's what I'd like to introduce to you right now. What we're also going to have every time we take a limit to the right and to the left of C, we're going to have two conceptual things here. We're going to have on the left the value C minus delta. We talked a little bit about delta in the last video. And then to the right, we're going to have a little C plus delta. And delta just stands for as we get very, very, very close to our C value, to the actual x value of our limit. And then on the y-axis, we're going to have similar concepts going on. Sorry, my dotted lines are not the best. I do apologize. Let me make those a little bit more bold for you. Okay, that's better. Awesome. Okay, and conceptually, again, we do have similar things going on with our y-axis, where above our limit value, we have the L plus the Greek letter epsilon, which just looks like a little backwards 3. And then below it, we have our limit minus the epsilon. And just like delta meant really close to our x, epsilon means really close to our y. Okay. And what we basically know about limits already is this. We're just going to kind of write out our thoughts like we've been doing. I just write down with me as we go along here. We know that a limit exists when our y values, our f of x, get very close to L, that value of our limit, and at the same time, as our x values, our x gets very close to C. And typically we know in that limit notation on the bottom of the word lim, we have the x and the arrow C as x gets very close to C. We know that that's what that means. Now, what we're going to do next is we're going to take all of these words and we're going to actually use these deltas and these epsilons, and we're going to define it a little bit better mathematically, and we're going to use some absolute values to do so. Because we aren't interested in negatively close, right? Negatively close values. So we're going to use absolute value in our expressions. Right? We don't really care. If we picked a point over here, we wouldn't say that it was negative distance away from our point. We would still talk about it in the positive terms. So we would say what we're interested in is as f of x gets very close to L, well, gets very close to, we can just use subtraction to express that. So we're going to start with our absolute value, our f of x minus L. We know that as f of x gets very close to L, as this value gets really, really small, right, as our graph minus our limit gets really, really, really small, we can just say is small when, similarly, x minus our c, but again, not negative, so we use absolute value, when absolute value of x minus our c is also very small. Can you see that over on the call? Okay, good. So, all right, we're getting closer. We're using some math terms. This is looking good so far, but we really want to incorporate our epsilons and our deltas into this, and we can if we think about it. Remember, we're using delta, which looks like that weird kind of S-shaped thing, for our x values. And we're going to use epsilon, that weird looking backwards 3, for our y values. And what we can say, we can define this part is small and is small using delta and epsilon. So we want our graph, our x, as it gets close to c, we want to be within this range here, right? That's what we're talking about. We're talking about being in between the lines here and in between the lines here. So what we're saying is we want our x minus our c, our absolute value, to be within this. And how we say that in math is that we want it to be less than our delta values. So, similarly, with our y's, we want our f of x minus our L to be inside this range, so we want our f of x minus our L, that absolute value, to be less than our epsilon values. And if we write that out, so far we've got this. Our absolute value of f of x minus L is very small, or is less than the epsilon, when x is also very small, or when, as x approaches c, is less than the delta. Right? That would define very small pretty well. Here's the thing. We have to add one more specification to this definition. One more specification. We know whenever we're finding a limit, we talked at the very, very, very beginning when we first talked about limits, that it does us no good to have x actually be exactly equal to c. The definition of a limit, the idea of a limit, is to get very close but not equal to c. So let's write out that thought. We know that x can't equal c. And we know that the limits will only exist when we can have these epsilons and these deltas in the first place, correct? Again, it does us no good to be exactly on that point. We need to have some approximation room. So that approximation room has to exist. That approximation room for our epsilons and for our deltas can't be equal to 0. So we know that our limits exist only when our epsilons are greater than 0 and when our deltas are greater than 0. All right, so we have some specifications we don't have to throw in here, and here's how we're going to do that. We still need to say that f of x minus L is less than the epsilon when, here's when we talk about x can't equal c, when that value, the difference between x minus c, getting very close, is greater than 0. And that's it, you guys. This is our formal definition of a limit. And again, I know it looks kind of confusing, but just remember all it's saying is that when when our y values get very, very small, very, very close to our limit, so do our x values, right? If our y values are able to do that, then so are our x's, and they're able to meet in the middle at our limit value. That's all it's saying. All right. So let's do, pardon me, let me flip through some notes here, get to another page. Okay, let's do an example of this, and then I'll stop talking at you for this video. Okay, so this topic is finding a delta for a given epsilon. Okay, finding a delta for a given epsilon. And here's an example. So, say we are given that the limit as x approaches 3 for the function 2x minus 5 equals 1. We know what the limit is. Find a delta such that pardon me. Okay, such that the absolute value of 2x minus 5 minus 1 is less than 0.01. Whenever 0 is less than the absolute value of x minus 3 minus our delta. Okay. First, let's just discuss what they've done for us. They got this piece from that f of x minus the L, right? Here's our f of x. Here's our L, what the limit was equal to. And they are telling us that our epsilon value is 0.01. They already gave that to us. And now our job is to find a delta value within those ranges. So basically what we're trying to find, I'll draw you guys a picture. Maybe this will help us out a little bit. Okay. Let's say we're at 1, 2, 3, perhaps 4. Okay. And then we're up at 1 and 2. So 2 and 4. Okay. Here's our graph. And if we were to graph this line, we'd have a point at 3, 1. And our graph would kind of be going up like this. It's not perfect, but don't worry about that right now. We're just trying to drive home a point here. Here's what they have given us. They've told us that here's our limit, and we don't know these pieces yet. These little pieces right here are plus our plus delta and our minus delta, right? We don't know what those values are. What our delta is, the change from the C to the left and to the right. However, they told us this piece. They told us that it goes up 0.01 and that it goes down 0.01, and we find our limit in there. So we can just kind of like shade that in. And now our job is to find the x values that will sort of overlap with this, right? When those y values are that small, oh, pardon me, let me show you this up close a little bit better. There we go. So when our y values are that small, that close to the point, it's our job now to find the corresponding x values that are also that close. And that will cross those lines vertically where they cross horizontally, if that makes sense. Just kind of a picture of what we're trying to find. Okay, and we can start to do this by simplifying this whole piece here. So what we're going to start off with is simplify 2x minus 5 minus 1. Here's the thing. Algebra tells us we can just subtract this negative 5 minus 1. And we can say that this is the same thing as the absolute value of 2x minus 6. And hang on, there's one more thing we can do here. There's a 2 here and there's a 2 in here, so we can factor out a 2. And then we get x minus 3. 2 outside the absolute value of x minus 3 is less than 0.001. Or pardon me, 0.01, 0.01. Okay, and we can take this a step further, and we can say that absolute value of x minus 3 is less than 0.01 over 2. And here's why this is helpful to find. Look at what they defined delta as in the first place. Absolute value of x minus 3 is less than delta. Well, hang on. We just found that absolute value of x minus 3 is less than 0.01 over 2. So, by substitution, we have just found that delta is equal to 0.01 over 2, or 0.005. Okay, so now if you go back to our little picture here, we found what we needed to know. We found that for the change ranges in our y's from 0.01 up and 0.01 down correspond with a change in our x values, our c values, of 0.005 either way. So that's pretty cool. Here's the thing. It's also important to note that it could be 0.005 or smaller. So say that we filled this in, right? This is, we'll fill in the values negative 0.005 and plus 0.005 from C. If we went further in, we'd still be okay. We'd still be touching those horizontal lines up there that we need to be touching. However, if we went bigger, we would not be in the same ranges anymore. That would not be okay. So that's not all right. But making the value smaller would still work for our deltas. And I believe that's everything from my notes, everything that I had to show you. So that's it for this video, and we'll see you in class tomorrow.